In mathematics, the logarithm of a number is the exponent to which another fixed value, the base, must be raised to produce that number. For example, the logarithm of 1000 to base 10 is 3, because 10 to the power 3 is 1000, 1000 equals 10 a euro 10 a euro 10 equals 103. More generally, for any two real numbers b and x where b is positive and b a per mil 1. The logarithm to base 10 is called the common logarithm and has many applications in science and engineering. The natural logarithm has the irrational number e as its base. Its use is widespread in pure mathematics, especially calculus. The binary logarithm uses base 2 and is prominent in computer science. Logarithms were introduced by John Napier in the early 17th century as a means to simplify calculations. They were rapidly adopted by navigators, scientists, engineers, and others to perform computations more easily, using slide rules and logarithm tables. Tedious multi-digit multiplication steps can be replaced by table lookups and simpler addition because of the fact important in its own right that the logarithm of a product is the sum of the logarithms of the factors. Provided that b, x and y are all positive and b a per mil 1. The present-day notion of logarithms comes from Leonhard Euler, who connected them to the exponential function in the 18th century. Logarithmic scales reduce wide-ranging quantities to smaller scopes. For example, the decibel is a logarithmic unit quantifying sound pressure and signal power ratios. In chemistry, pH is a logarithmic measure for the acidity of an aqueous solution. Logarithms are commonplace in scientific formulae, and in measurements of the complexity of algorithms and of geometric objects called fractals. They describe musical intervals, appear in formulae counting prime numbers, inform some models in psychophysics, and can aid in forensic accounting. In the same way as the logarithm reverses exponentiation, the complex logarithm is the inverse function of the exponential function applied to complex numbers. The discrete logarithm is another variant. It has applications in public key cryptography. Motivation and definition. The idea of logarithms is to reverse the operation of exponentiation, that is raising a number to a power. For example, the third power of 2 is 8, because 8 is the product of three factors of 2. It follows that the logarithm of 8 with respect to base 2 is 3, so log 2a8 equals a3. Exponentiation, the third power of some number b is the product of three factors of b. More generally, raising b to the nth power, where n is a natural number, is done by multiplying n factors of b. The nth power of b is written bn, so that exponentiation may be extended to by, where b is a positive number and the exponent y is any real number. For example, bar 1 is the reciprocal of b, that is, 1/b. Definition: the logarithm of a positive real number x with respect to base b, a positive real number not equal to 1, is the exponent by which b must be raised to yield x. In other words, the logarithm of x to base b is the solution y to the equation. The logarithm is denoted log(b), x. In the equation y equals log(b), x, the value y is the answer to the question to what power must b be raised, in order to yield x. This question can also be addressed for complex numbers, which is done in section complex logarithm, and this answer is much more extensively investigated in the page for the complex logarithm. Examples: for example, log 2, 16, equals 4, since 24 equals 2 euro a, 2 euro a euro 2 euro a euro 2 equals 16. Logarithms can also be negative. Since a third example, log 10, 150, is approximately 2.176, which lies between 2 and 3, just as 150 lies between 102 equals 100 and 103 equals 1000. Finally, for any base b, log(b), b equals 1 and log(b), 1 equals 0, since b1 equals b and b0 equals 1, respectively. Logarithmic identities. Several important formulas, sometimes called logarithmic identities or log laws, relate logarithms to one another. product, quotient, power and root. The logarithm of a product is the sum of the logarithms of the numbers being multiplied. The logarithm of the ratio of two numbers is the difference of the logarithms. The logarithm of the pth power of a number is p times the logarithm of the number itself. The logarithm of a pth root is the logarithm of the number divided by p. The following table lists these identities with examples. Each of the identities can be derived after substitution of the logarithm definitions x equals b log x, and or y equals b log y, in the left-hand sides. Change of base. The logarithm log x can be computed from the logarithms of x and b with respect to an arbitrary base k using the following formula. Typical scientific calculators calculate the logarithms to bases 10 and e. Logarithms with respect to any base b can be determined using either of these two logarithms by the previous formula. Given a number x and its logarithm log x, to an unknown base b, the base is given by particular bases. Among all choices for the base, 3 are particularly common. These are bar equals a10, bar equals ae, and bar equals a2. In mathematical analysis, the logarithm to base e is widespread because of its particular analytical properties explained below. On the other hand, base 10 logarithms are easy to use for manual calculations in the decimal number system. Thus, log 10, x, is related to the number of decimal digits of a positive integer x. The number of digits is the smallest integer strictly bigger than log 10, x. For example, log 10, 1430, is approximately 3.15. The next integer is 4, which is the number of digits of 1430. The logarithm to base 2 is used in computer science, where the binary system is ubiquitous, and in music theory, where a pitch ratio of 2 is ubiquitous and the cent is the binary logarithm of the ratio between two adjacent equally tempered pitches. The following table lists common notations for logarithms to these bases and the fields where they are used. Many disciplines write log x instead of log x, when the intended base can be determined from the context. The notation blog x also occurs. The ISO notation column lists designations suggested by the International Organization for Standardization. History, predecessors. The Babylonians sometime in 2000 1600 BC may have invented the quarter square multiplication algorithm to multiply two numbers using only addition, subtraction and a table of quarter squares. However, it could not be used for division without an additional table of reciprocals. Large tables of quarter squares were used to simplify the accurate multiplication of large numbers from 1817 onwards until this was superseded by the use of computers. The Indian mathematician Virasna worked with the concept of Ardhakida, the number of times a number of the form 2n could be halved. For exact powers of 2, this is the logarithm to that base, which is a whole number. For other numbers, it is undefined. He described relations such as the product formula and also introduced integer logarithms in base 3 and base 4. Michael Stifler published Arithmetica Integra in Nuremberg in 1544. Which contains a table of integers and powers of 2 that has been considered an early version of a logarithmic table. In the 16th and early 17th centuries an algorithm called prostaphyresis was used to approximate multiplication and division. This used the trigonometric identity, or similar, to convert the multiplications to additions and table lookups. However, logarithms are more straightforward and require less work. It can be shown using Euler's formula that the two techniques are related. From Napier to Euler. The method of logarithms was publicly propounded by John Napier in 1614, in a book titled Miraficare Logarithmorum Canonis Descriptio. Just bar 1/4 AGI independently invented logarithms but published 6 years after Napier. Johannes Kepler, who used logarithm tables extensively to compile his ephemeris and therefore dedicated it to Napier, remarked. The accent in calculation led Justus Bigius, just bar 1/4 AGI on the way to these very logarithms many years before Napier's system appeared. But Instead of rearing up his child for the public benefit, he deserted it in the birth. By repeated subtractions, Napier calculated L for L ranging from 1 to 100. The result for L equals 100 is approximately 0.99999 equals 1/10⁵. Napier then calculated the products of these numbers with 107, 1/10⁵, L for L from 1 to 50, and did similarly with 0.9998 /ml 20 and 0.9 /ml 0.99520. These computations, which occupied 20 years, allowed him to give, for any number n from 5 to 10 million, the number L that solves the equation. Napier first called L an artificial number, but later introduced the word logarithm to mean a number that indicates a ratio, I cubed II meaning proportion, and a 1/4 euro II to the first I 1/4 IOI meaning number. In modern notation, the relation to natural logarithms is where the very close approximation corresponds to the observation that. The invention was quickly and widely met with acclaim. The works of Bonaventura Cavalieri, Edmund Wingate, Xufeng Zhou, and Johannes Kepler's Chilia's Logarithmorum helped spread the concept further. In 1647, Gras copyright Goya de St. Vincent related logarithms to the quadrature of the hyperbola, by pointing out that the area f, t, under the hyperbola from x equals 1 to x equals t satisfies. The natural logarithm was first described by Nicholas Mercator in his work Logarithmotechnia published in 1668, although the mathematics teacher John Spadell had already in 1619 compiled a table of what were effectively natural logarithms, based on Napier's work. Around 1730, Leonhard Euler defined the exponential function and the natural logarithm by. Euler also showed that the two functions are inverse to one another. Logarithm tables, slide rules, and historical applications. By simplifying difficult calculations, logarithms contributed to the advance of science, and especially of astronomy. They were critical to advances in surveying, celestial navigation, and other domains. Pierre-Simon Laplace called logarithms an admirable artifice which, by reducing to a few days the labor of many months, doubles the life of the astronomer, and spares him the errors and disgust inseparable from long calculations. A key tool that enabled the practical use of logarithms before calculators and computers was the Table of Logarithms. The first such table was compiled by Henry Briggs in 1617, immediately after Napier's invention. Subsequently, tables with increasing scope and precision were written. These tables listed the values of log(b), x, and bx for any number x in a certain range, at a certain precision, for a certain base b. For example, Briggs' first table contained the common logarithms of all integers in the range 1/1000, with a precision of 8 digits. As the function f, x, equals bx is the inverse function of log(b), x, it has been called the anti-logarithm. The product and quotient of two positive numbers c and d were routinely calculated as the sum and difference of their logarithms. The product CD or quotient CD came from looking up the anti-logarithm of the sum or difference, also via the same table. And for manual calculations that demand any appreciable precision, performing the lookups of the two logarithms, calculating their sum or difference, and looking up the anti-logarithm is much faster than performing the multiplication by earlier methods such as prostaphylleresis, which relies on trigonometric identities. Calculations of powers and roots are reduced to multiplications or divisions and lookups by and. Many logarithm tables give logarithms by separately providing the characteristic and mantissa of x, that is to say, the integer part and the fractional part of log 10, x. The characteristic of 10ax is 1 plus the characteristic of x, and their significans are the same. This extends the scope of logarithm tables. Given a table listing log 10, x, for all integers x ranging from 1 to 1000, the logarithm of 3542 is approximated by. Another critical application was the slide rule, a pair of logarithmically divided scales used for calculation, as illustrated here. The non-sliding logarithmic scale, Gunter's rule, was invented shortly after Napier's invention. William Orchard enhanced it to create the slide rule a pair of logarithmic scales movable with respect to each other. Numbers are placed on sliding scales at distances proportional to the differences between their logarithms. Sliding the upper scale appropriately amounts to mechanically adding logarithms. For example, adding the distance from 1 to 2 on the lower scale to the distance from 1 to 3 on the upper scale yields a product of 6, which is read off at the lower part. The slide rule was an essential calculating tool for engineers and scientists until the 1970s, because it allows, at the expense of precision, much faster computation than techniques based on tables. Analytic properties. A deeper study of logarithms requires the concept of a function. A function is a rule that, given one number, produces another number. An example is the function producing the xth power of b from any real number x, where the base b is a fixed number. This function is written. Logarithmic function. To justify the definition of logarithms, it is necessary to show that the equation has a solution x and that this solution is unique, provided that y is positive and that b is positive and unequal to 1. A proof of that fact requires the intermediate value theorem from elementary calculus. This theorem states that a continuous function that produces two values m and n also produces any value that lies between m and n. A function is continuous if it does not jump, that is, if its graph can be drawn without lifting the pen. This property can be shown to hold for the function f, x, equals bx. Because f takes arbitrarily large and arbitrarily small positive values, any number y greater than 0 lies between f, x0, and f, x1, for suitable x0 and x1. Hence, the intermediate value theorem ensures that the equation f, x, equals y has a solution. Moreover, there is only one solution to this equation, because the function f is strictly increasing, or strictly decreasing. The unique solution x is the logarithm of y to base b, log y. The function that assigns to y its logarithm is called logarithm function or logarithmic function. The function log x is essentially characterized by the above product formula. More precisely, the logarithm to any base b greater than 1 is the only increasing function f from the positive reals to the reals satisfying f, b, equals 1 and inverse function. The formula for the logarithm of a power says in particular that for any number x. In prose, taking the xth power of b and then the base b logarithm gives back x. Conversely, given a positive number y, the formula says that first taking the logarithm and then exponentiating gives back y. Thus, the two possible ways of combining logarithms and exponentiation give back the original number. Therefore, the logarithm to base b is the inverse function of f, x, equals bx. Inverse functions are closely related to the original functions. Their graphs correspond to each other upon exchanging the x and the y coordinates, as shown at the right. A point on the graph of f yields a point on the graph of the logarithm and vice versa. As a consequence, log x diverges to infinity if x grows to infinity, provided that b is greater than 1. In that case, log x is an increasing function. For b less than 1, log x tends to minus infinity instead. When x approaches 0, log x goes to minus infinity for b greater than 1. Derivative and antiderivative. Analytic properties of functions pass to their inverses. Thus, as f, x, equals bx is a continuous and differentiable function, so is log y. Roughly, a continuous function is differentiable if its graph has no sharp corners. Moreover, as the derivative of f, x, evaluates to ln, b, bx by the properties of the exponential function, the chain rule implies that the derivative of log x is given by, that is, the slope of the tangent touching the graph of the base b logarithm at the point, equals 1 / ln b. In particular, the derivative of ln x is 1 / x, which implies that the antiderivative of 1 / x is ln x plus c. the derivative with a generalized functional argument f, x, is. The quotient at the right-hand side is called the logarithmic derivative of f. Computing f, x, by means of the derivative of ln, f, x is known as logarithmic differentiation. The antiderivative of the natural logarithm ln, x, is. Related formulas, such as antiderivatives of logarithms to other bases, can be derived from this equation using the change of bases. Integral representation of the natural logarithm. The natural logarithm of t agrees with the integral of 1/z dx from 1 to t. In other words, ln, t, equals the area between the x-axis in the graph of the function 1/x, ranging from x equals 1 to x equals t. This is a consequence of the fundamental theorem of calculus and the fact that derivative of ln, x, is 1/x. The right-hand side of this equation can serve as a definition of the natural logarithm. Product and power logarithm formulas can be derived from this definition. For example, the product formula ln, 2, equals ln, t, plus ln, u, is deduced as. The equality splits the integral into two parts, while the equality is a change of variable. In the illustration below, the splitting corresponds to dividing the area into the yellow and blue parts. Rescaling the left-hand blue area vertically by the factor t and shrinking it by the same factor horizontally does not change its size. Moving it appropriately, the area fits the graph of the function f, x, equals 1/x again. Therefore, the left-hand blue area, which is the integral of f, x, from t to 2 is the same as the integral from 1 to u. This justifies the equality with a more geometric proof. The power formula ln, tr, equals r ln, t, may be derived in a similar way. The second equality uses a change of variables, w equals x1 per Rankine. The sum over the reciprocals of natural numbers is called the harmonic series. It is closely tied to the natural logarithm, as n tends to infinity, the difference converges to a number known as the Euler or Euro-Mascaroni constant. This relation aids in analyzing the performance of algorithms such as quicksort. There is also another integral representation of the logarithm that is useful in some situations. This can be verified by showing that it has the same value at x equals 1, and the same derivative. Transcendents of the logarithm, real numbers that are not algebraic are called transcendental. For example, I euro and d are such numbers, but is not. Almost all real numbers are transcendental. The logarithm is an example of a transcendental function. The Giel-Fonda-Euro-Schneider theorem asserts that logarithms usually take transcendental, that is, difficult values. Calculation. Logarithms are easy to compute in some cases, such as log 10, 1000 equals 3. In general, logarithms can be calculated using power series or the arithmetic geometric mean, or be retrieved from a pre-calculated logarithm table that provides a fixed precision. Newton's method, an iterative method to solve equations approximately, can also be used to calculate the logarithm, because its inverse function, the exponential function, can be computed efficiently. Using lookup tables, Chordic-like methods can be used to compute logarithms if the only available operations are addition and bit shifts. Moreover, the binary logarithm algorithm calculates LB, x, recursively based on repeated squarings of x, taking advantage of the relation power series, Taylor series. For any real number z that satisfies 0, z less than 2, the following formula holds. This is a shorthand for saying that ln, z, can be approximated to a more and more accurate value by the following expressions. For example, with z equals 1.5, the third approximation yields 0.4167, which is about 0.011 greater than ln, 1.5 equals 0.405465. This series approximates ln, z, with arbitrary precision, provided the number of summands is large enough. In elementary calculus, ln, z, is therefore the limit of the series. It is the Taylor series of the natural logarithm at z equals 1. The Taylor series of ln z provides a particularly useful approximation to ln, 1 plus z, when z is small, z1, since then. For example, with z equals 0.1, the first-order approximation gives ln, 1.1 a parmel 0.1, which is less than 5% off the correct value 0.0953. More efficient series, another series is based on the area hyperbolic tangent function. For any real number z greater than 0. Using the sigma notation, this is also written as. This series can be derived from the above Taylor series. It converges more quickly than the Taylor series, especially if z is close to 1. For example, for z equals 1.5, the first three terms of the second series approximate ln, 1.5 with an error of about 3a, 10^6. The quick convergence for z close to 1 can be taken advantage of in the following way, given a low accuracy approximation ya parmel ln, z, and putting the logarithm of z is. The better the initial approximation y is, the closer a is to 1, so its logarithm can be calculated efficiently. A can be calculated using the exponential series, which converges quickly provided y is not too large. Calculating the logarithm of larger z can be reduced to smaller values of z by writing z equals a10b, so that ln, z, equals ln, a, plus ba ln, 10. A closely related method can be used to compute the logarithm of integers. From the above series, it follows that if the logarithm of a large integer n is known, then this series yields a fast converging series for log, n plus 1. Arithmetic geometric mean approximation. The arithmetic geometric mean yields high precision approximations of the natural logarithm ln, x, is approximated to a precision of 2ap by the following formula. Here m denotes the arithmetic geometric mean. It is obtained by repeatedly calculating the average and the square root of the product of two numbers. Moreover, m is chosen such that both the arithmetic geometric mean and the constants I euro and ln, 2, can be calculated with quickly converging series. Applications. Logarithms have many applications inside and outside mathematics. Some of these occurrences are related to the notion of scale invariance. For example, each chamber of the shell of a nautilus is an approximate copy of the next one, scaled by a constant factor. This gives rise to a logarithmic spiral. Benford's law on the distribution of leading digits can also be explained by scale invariance. Logarithms are also linked to self-similarity. For example, logarithms appear in the analysis of algorithms that solve a problem by dividing it into two similar smaller problems and patching their solutions. The dimensions of self-similar geometric shapes, that is, shapes whose parts resemble the overall picture, are also based on logarithms. Logarithmic scales are useful for quantifying the relative change of a value as opposed to its absolute difference. Moreover, because the logarithmic function log, x, grows very slowly for large x, logarithmic scales are used to compress large-scale scientific data. Logarithms also occur in numerous scientific formulas, such as the Tsikhovsky rocket equation, the Fensk equation, or the Nernst equation. Logarithmic scale. Scientific quantities are often expressed as logarithms of other quantities, using a logarithmic scale. For example, the decibel is a logarithmic unit of measurement. It is based on the common logarithm of radius euro 10 times the common logarithm of a power ratio or 20 times the common logarithm of a voltage ratio. It is used to quantify the loss of voltage levels in transmitting electrical signals, to describe power levels of sounds in acoustics, and the absorbance of light in the fields of spectrometry and optics. The signal-to-noise ratio describing the amount of unwanted noise in relation to a signal is also measured in decibels. In a similar vein, the peak signal-to-noise ratio is commonly used to assess the quality of sound and image compression methods using the logarithm. The strength of an earthquake is measured by taking the common logarithm of the energy emitted at the quake. This is used in the moment magnitude scale or the Richter scale. For example, A 5.0 earthquake releases 10 times and a 6.0 releases 100 times the energy of a 4.0. Another logarithmic scale is apparent magnitude. It measures the brightness of stars logarithmically. Yet another example is pH in chemistry. pH is the negative of the common logarithm of the activity of hydronium ions. The activity of hydronium ions in neutral water is 10^7 a molar La1, hence a pH of 7. Vinegar typically has a pH of about 3. The difference of 4 corresponds to a ratio of 104 of the activity, that is, vinegar's hydronium ion activity is about 10^3 a molar La1. Semilog graphs use the logarithmic scale concept for visualization. One axis, typically the vertical one, is scaled logarithmically. For example, the chart at the right compresses the steep increase from 1 million to 1 trillion to the same space as the increase from 1 to 1 million. In such graphs, exponential functions of the form f, x, equals aabx appear as straight lines with slope equal to the logarithm of b. Log-log graphs scale both axes logarithmically, which causes functions of the form f, x, equals aaxk to be depicted as straight lines with slope equal to the exponent k. This is applied in visualizing and analyzing power laws. Psychology. Logarithms occur in several laws describing human perception. Hicks' law proposes a logarithmic relation between the time individuals take for choosing an alternative and the number of choices they have. Fitz's law predicts that the time required to rapidly move to a target area is a logarithmic function of the distance to and the size of the target. In psychophysics, the Weber-Fechner law proposes a logarithmic relationship between stimulus and sensation such as the actual versus the perceived weight of an item a person is carrying. Psychological studies found that individuals with little mathematics education tend to estimate quantities logarithmically, that is, they position a number on an unmarked line according to its logarithm, so that 10 is positioned as close to 100 as 100 is to 1000. Increasing education shifts this to a linear estimate in some circumstances, while logarithms are used when the numbers to be plotted are difficult to plot linearly. Probability theory and statistics. Logarithms arise in probability theory. The law of large numbers dictates that, for a fair coin, as the number of coin tosses increases to infinity, the observed proportion of heads approaches 1/2. The fluctuations of this proportion about 1/2 are described by the law of the iterated logarithm. Logarithms also occur in log-normal distributions. When the logarithm of a random variable has a normal distribution, the variable is said to have a log-normal distribution. Log-normal distributions are encountered in many fields, wherever a variable is formed as the product of many independent positive random variables, for example in the study of turbulence. Logarithms are used for maximum likelihood estimation of parametric statistical models. For such a model, the likelihood function depends on at least one parameter that must be estimated. A maximum of the likelihood function occurs at the same parameter value as a maximum of the logarithm of the likelihood, because the logarithm is an increasing function. The log likelihood is easier to maximize, especially for the multiplied likelihoods for independent random variables. Benford's law describes the occurrence of digits in many data sets, such as heights of buildings. According to Benford's law, the probability that the first decimal digit of an item in the data sample is d equals log 10, d plus 1, a log 10, d, regardless of the unit of measurement. Thus, about 30% of the data can be expected to have 1 as first digit, 18% start with 2, etc. Auditors examine deviations from Benford's law to detect fraudulent accounting. Computational complexity. Analysis of algorithms is a branch of computer science that studies the performance of algorithms. Logarithms are valuable for describing algorithms that divide a problem into smaller ones, and join the solutions of the subproblems. For example, to find a number in a sorted list, the binary search algorithm checks the middle entry and proceeds with the half before or after the middle entry if the number is still not found. This algorithm requires, on average, log 2, n, comparisons, where n is the list's length. Similarly, The merge-sort algorithm sorts an unsorted list by dividing the list into halves and sorting these first before merging the results. Merge-sort algorithms typically require a time approximately proportional to NA log n. The base of the logarithm is not specified here, because the result only changes by a constant factor when another base is used. A constant factor is usually disregarded in the analysis of algorithms under the standard uniform cost model. A function f, x, is said to grow logarithmically if f, x, is proportional to the logarithm of x. For example, any natural number n can be represented in binary form in no more than log 2, n, plus 1 bits. In other words, the amount of memory needed to store n grows logarithmically with n, entropy and chaos. Entropy is broadly a measure of the disorder of some system. In statistical thermodynamics, the entropy S of some physical system is defined as the sum is over all possible states I of the system in question, such as the positions of gas particles in a container. Moreover, pi is the probability that the state I is attained and k is the Boltzmann constant. Similarly, entropy in information theory measures the quantity of information. If a message recipient may expect any one of n possible messages with equal likelihood, then the amount of information conveyed by any one such message is quantified as log 2, n, bits. Lyapunov exponents use logarithms to gauge the degree of staticity of a dynamical system. For example, for a particle moving on an oval billiard table, even small changes of the initial conditions result in very different parts of the particle. Such systems are chaotic in a deterministic way, because small measurement errors of the initial state predictably led to largely different final states. At least one Lyapunov exponent of a deterministically chaotic system is positive. Fractals. Logarithms occur in definitions of the dimension of fractals. Fractals are geometric objects that are self-similar, small parts reproduce, at least roughly, the entire global structure. The Sierpinski triangle can be covered by 3 copies of itself, each having sides half the original length. This makes the Hausdorff dimension of this structure log 3/log 2, a permil 1.58. Another logarithm-based notion of dimension is obtained by counting the number of boxes needed to cover the fractal in question. Music. Logarithms are related to musical tones and intervals. In equal temperament, the frequency ratio depends only on the interval between 2 tones, not on the specific frequency, or pitch, of the individual tones. For example, the note A has a frequency of 440 Hz and B-flat has a frequency of 466 Hz. The interval between A and B-flat is a semitone, as is the one between B-flat and B. Accordingly, the frequency ratios agree. Therefore, logarithms can be used to describe the intervals. An interval is measured in semitones by taking the base 21/12 logarithm of the frequency ratio, while the base 21 1/1200 logarithm of the frequency ratio expresses the interval in cents, hundredths of a semitone. The latter is used for finer encoding, as it is needed for non-equal temperaments. Number theory. Natural logarithms are closely linked to counting prime numbers, an important topic in number theory. For any integer x, the quantity of prime numbers less than or equal to x is denoted I x. The prime number theorem asserts that I x is approximately given by, in the sense that the ratio of I x, and that fraction approaches 1 when x tends to infinity. As a consequence, the probability that a randomly chosen number between 1 and x is prime is inversely proportional to the numbers of decimal digits of x. A far better estimate of I x is given by the offset logarithmic integral function Li x, defined by the Riemann hypothesis. One of the oldest open mathematical conjectures, can be stated in terms of comparing I x and Li x. The Adesa-Eurocac theorem describing the number of distinct prime factors also involves the natural logarithm. The logarithm of n factorial, n equals 1 or 2a. an is given by. This can be used to obtain Stirling's formula, an approximation of n. for large N. Generalizations, complex logarithm. The complex numbers are solving the equation are called complex logarithms. Here, Z is a complex number. A complex number is commonly represented as Z equals X plus I, where X and Y are real numbers and I is the imaginary unit. Such a number can be visualized by a point in the complex plane, as shown at the right. The polar form encodes a non-zero complex number Z by its absolute value, that is, the distance to the origin, and an angle between the x-axis and the line passing through the origin and Z. This angle is called the argument of Z. The absolute value of Z is. The argument is not uniquely specified by Z. Both I and I equals I plus 2I euro are arguments of Z because adding 2I euro radians or 360 degrees to I corresponds to winding around the origin counterclockwise by a turn. The resulting complex number is again Z, as illustrated at the right. However, exactly one argument I satisfies AI euro I and IA per mole currency I euro. It is called the principal argument, denoted UG, Z, with a capital A. 2I euro. Using trigonometric functions sine and cosine, or the complex exponential, respectively, R and I are such that the following identities hold. This implies that the ATH power of E equals Z, where I is the principal argument UG, Z, and N is an arbitrary integer. Any such A is called a complex logarithm of Z. There are infinitely many of them, in contrast to the uniquely defined real logarithm. If n equals 0, A is called the principal value of the logarithm, denoted log, Z. The principal argument of any positive real number x is 0. Hence log, x, is a real number and equals the real logarithm. However, the above formulas for logarithms of products and powers do not generalize to the principal value of the complex logarithm. The illustration at the right depicts log, Z. The discontinuity, that is, the jump in the hue at the negative part of the x or real axis, is caused by a jump of the principal argument there. This locus is called a branch cut. This behavior can only be circumvented by dropping the range restriction on I. Then the argument of Z and, consequently, its logarithm become multi-valued functions. Inverses of other exponential functions, exponentiation occurs in many areas of mathematics and its inverse function is often referred to as the logarithm. For example, the logarithm of a matrix is the inverse function of the matrix exponential. Another example is the p-adic logarithm, the inverse function of the p-adic exponential. Both are defined via Taylor series analogous to the real case. In the context of differential geometry, the exponential map maps the tangent space at a point of a manifold to a neighborhood of that point. Its inverse is also called the logarithmic map. In the context of finite groups, exponentiation is given by repeatedly multiplying one group element B with itself. The discrete logarithm is the integer n solving the equation, where x is an element of the group. Carrying out the exponentiation can be done efficiently, but the discrete logarithm is believed to be very hard to calculate in some groups. This asymmetry has important applications in public key cryptography, such as for example in the Diffie-Euro-Hellman key exchange, a routine that allows secure exchanges of cryptographic keys over unsecured information channels. Zek's logarithm is related to the discrete logarithm in the multiplicative group of non-zero elements of a finite field. Further logarithm-like inverse functions include the double logarithm ln, x, the super or hyper-4 logarithm, the Lambert W function, and the logit. They are the inverse functions of the double exponential function, titration, of f, w, equals wo, and of the logistic function, respectively. Related concepts, from the perspective of pure mathematics, the identity log, CD, equals log, C, plus log, D, expresses a group isomorphism between positive reals under multiplication and reals under addition. Logarithmic functions are the only continuous isomorphisms between these groups. By means of that isomorphism, the Haar measure dx on the reals corresponds to the Haar measure dx on the positive reals. In complex analysis and algebraic geometry, Differential forms of the form DFF are known as forms with logarithmic poles. The polar logarithm is the function defined by. It is related to the natural logarithm by Lie 1, z, equals ln, 1az. Moreover, Lie's 1 equals the Riemann zeta function I paragraph s. See also, exponential function, index of logarithm articles, notes. References. External links, media related to logarithm at Wikimedia Commons, the dictionary definition of logarithm at Wiktionary, Khan Academy, Logarithms, free online micro-lectures, Haswinkel, Michiel, ed., Logarithmic Function, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-Fora, Colin Byfleet, Educational Video on Logarithms, retrieved 122,010. Edward Wright, Translation of Napier's work on logarithms, retrieved 122,010a.